we were discussing the property of compactness in the last class. Let us again recall that we have defined that set is compact means every open cover of that set should have a finite subcover. Okay. We have seen some examples of compact sets, and then we have also seen a few properties, namely that every compact set is closed, okay. And till now the definitions of compact sets are in terms of open sets, okay. We shall also consider some criteria about compactness in terms of closed sets, but before that let us complete one theorem which we started yesterday. That was the following. Suppose XD is a metric space and A is a compact set in X, and B is a closed subset of A. Then B is compact. Okay. In other words, so closed subset of a compact set is always compact. So let us look at the proof. As usual, to prove that any set is compact, we need to show that every open cover has a finite subcover. So start with an open cover of B. So let us say that let Gi, I belonging to I, be an open cover of B, okay. Again let me repeat that this means that each Gi is open, okay, and another thing is that B is contained in the union of Gi, okay. Alright. Now suppose you take this Gi, then this is a cover for B, okay, but we are given that A is compact, okay, that property has to be used somehow, okay. That means we have to construct a cover of A, then we can get its finite subcover using the compactness of A, okay. But this union of Gi covers only B, okay. So what about the points outside B? Well, those are not covered by this, but what we can say is that we are given that B is closed, okay. That means its complement is open, okay, its complement is open. So B is closed means this X minus B is open, okay. Alright. Now the idea is simply this: suppose I add this open set to this family, will that cover A? Right? Because those points which are in B, those are already in they are already in Gi. Those which are outside B, those will be in X minus B, okay. So what you can say is that this Gi, I belonging to I, then union the singleton X minus B, this is an open cover of A, okay, is an open cover of A. Open cover of A, okay, and since A is compact, this should have a finite subcover, okay, and okay, since A is compact, it has a finite subcover. But that finite subcover is not a subcover of this, okay, but it is a subcover of this new family, okay. But what is the difference? Only difference is this additional set, okay, only difference is this additional set. So that subcover may or may not contain this, okay? But does not matter, whichever is the case, we shall show that anyway it will be a subcover of A, it will be a subcover of A, so has a finite subcover. Let us say say gi1, gi2, say gin, and perhaps this x minus b. Okay, right. This may or may not be there. Okay, this may or may not be there. It doesn't matter. If it is not there, if x minus b is not there, then these gi1, gi2, gin cover b. Right? See, whatever is since b is contained in a, b is contained in a, any cover of a is also cover of b, right. So since okay, since this is a cover of a, it is also a cover of b. Okay. Only problem will be that if this finite subcover contains this set, that is not a subcover of this original family that you started with. Okay, that is the only problem. Okay? If this finite subcover does not contain this set, there is no problem. Okay, then this subcover will contain only gi1, gi2, gin, that is already a subcover of this family, and that is a cover of b. So we have proved that every open cover has a finite subcover. Only question is what is to be done if this finite subcover also contains this set x minus b. It is obvious what is to be done. Okay, just remove that set from this, just remove that set because this is a cover of a, we are not interested in the cover of a, what we want is cover of b. Okay, obviously this is not going to contain any point of b. Okay, so even if you remove this open set from this, remaining sets will also cover b. Okay, is that clear? So that proves that, and then these remaining set are coming from this family. Okay, right? So whichever is the case, we have proved that every open cover has a finite subcover. Is that clear? Okay, then we shall also discuss one more property of the compact set. So far we have proved that every compact set is closed. Okay, alright. Before going to that property, let us also characterize this compactness in terms of closed sets. Okay, and to do that, it is convenient to discuss the whole metric space instead of a subset. Okay, alright. Let me first give some definition. So suppose you have a family of sets. Let us say some family ai, I belonging to I. Okay, I is any big I is any indexing set. We say that such a family has a finite intersection property. Okay, that is what we want to say. We say that such a family has a finite intersection property. Okay, we say that a family of sets this ai, I belonging to I, has a finite intersection property. Okay, has a finite intersection property. Okay, there is a standard short form used for this, FIP, finite intersection property. Okay, it is clear from the name what it should mean. Okay, finite intersection property means if you take any finite subfamily of this, then that has a non-empty intersection. Okay, that is the meaning of saying that finite intersection property. Okay, we said has a finite intersection property if every finite subfamily okay, let me give some notation for this family. Suppose I call this family script A. Okay, if every finite subfamily of script A has a non-empty intersection, okay, of course we are not saying that the intersection over the whole family is non-empty, that may or may not be the case. Okay, but what is said is that if you take any collection, any finite collection of sets from here, say ai1, ai2, ain, etc., then the intersection over that finite subfamily should be non-empty. Okay, that is called, if a family has that property, if a family of sets has that property, we say that the family has finite intersection property. is clear. Okay. What is an obvious example of a family with this kind of property? We have seen earlier what we had called a decreasing sequence of sets. Okay. Suppose it is a sequence of set A1 contains A2, A2 contains A3, etc., etc. Okay, and suppose all of them are non-empty. Okay, then if you take intersection over any finite subfamily, okay, that intersection will be smallest among those sets, right? Right. For example, say A1 intersection A2 will be A2, okay, or A1 intersection A2 intersection A10, that will be A10, okay, whatever, once it is a decreasing family of sets. So decreasing family of sets in which each set is non-empty will have this finite intersection property, okay, but of course such a family may not have the property that intersection over the whole family is non-empty, that may or may not be true. Okay. Now where does compactness come into picture? What we can show is that in a compact, suppose a matrix space is compact, and if you take a family of closed sets which has a finite intersection property, then intersection over the entire family is also non-empty. Okay, intersection over the entire family is also non-empty. Okay, and this is equivalent to compactness. Okay, equivalent to compactness. So that is a theorem. Okay. And as I said, it is convenient to write this theorem in terms of the whole matrix space X instead of taking some subset of X. And we have seen earlier that that makes no difference whether you take a compact subset of a matrix space or talk of compactness of the whole space, that is more or less same. Okay, it makes no difference. So let us say that X is a matrix space. Okay, then X is compact if and only if every family of closed sets with finite intersection property. Okay, suppose you take a family of closed sets with finite intersection property, then intersection over the whole family is non-empty. Okay, so I have simply said every family of closed sets with finite intersection property has non-empty intersection. Okay, all right, and the proof involves actually just only one idea. Okay, namely that a set is open if and only if its complement is closed. Okay, right, and complements of the unions are intersections. Okay, these are the only ideas used. Okay, so okay, let us say, let us take this way. Okay, suppose X is compact and we want to prove that every family of closed sets with non-empty intersection has a with finite intersection property has a non-empty intersection. So start with a family of closed sets with finite intersection property. Okay, so let us say that let AI I belonging to I be a family of closed sets with finite intersection property. Okay, then we want to show that intersection over the whole family is non-empty. Okay, intersection over the whole family is non-empty. Okay. Suppose this is false. Okay, suppose this is false. Okay, so if intersection over AI I belonging to I is empty, okay, if intersection of AI I belong to I is empty, what should happen? What can we say about the complements of AI? Suppose this intersection is empty, its complement should be whole of X. Okay, and that should be nothing but union of AI complements, right? Okay, then what we can say is that then X is equal to union over I belonging to I X minus AI, right? Okay, but each of this x minus ai is open, right, each of this x minus ai is open and their union is x, that means this is an open cover for x, okay, that is what we can say is that is x minus ai, I belonging to I is an open cover of x. Now what is, how to proceed after this is obvious, okay, we have assumed that x is compact, okay, so every open cover must have a finite subcover, okay, so okay I will continue there. So what is argument, since x is compact, this open cover consisting of complements of ai must have a finite subcover, okay, which is same as saying that there should exist finite number of indices, let us say i1 i2 in, such that x minus a i1 x minus a i2 etc., that should cover x, okay. That is there exists, let us say i1 i2 in I such that x is contained in, or which is same as saying that x is equal to, because x is the whole space, okay, x is equal to union x minus a I k going from 1 to n. Alright, okay. Now what is the meaning of this? If x is the union of this x minus aik, okay, suppose I take again the complements of both sides, complement of this will be empty, okay, and what will be the complement of this? It will be the intersection of aik, k going from 1 to n, okay. So this, that is, this means phi is intersection aik, k going from 1 to n, okay, alright, okay, and that contradicts this finite intersection. We have assumed that ai is a family with a finite intersection property, and now we have produced a finite subfamily ai1 ai2 ai which has empty intersection, right, okay. So what this shows that if x is compact, then every family of closed sets with finite intersection property must have non-empty intersection, okay, alright, okay. What is the converse? Converse is that suppose a matrix space has this property that every family of closed sets with finite intersection property has non-empty intersection, then we should prove that x is compact, okay. Okay, what I will do is I shall leave that part of the proof to you as an exercise, okay. You will understand how to proceed, okay. To show that x is compact, you start with any open cover, okay, and then you have to show that it has a finite subcover, okay. Then whatever open cover you start, you take the complements, okay, and show that that family of closed sets has finite intersection property, okay, right, and then using basically again the principles involved are the same, that is complement of a closed set is open and vice versa, okay, and then complements of these unions is intersection and that kind of things, okay. So basic elementary set theory and this fact that a set is open if and only if its complement is closed, okay. Using these two things you will be able to prove this, okay. Now as I said that obvious examples of the families with the finite intersection property are the decreasing sequences of sets, okay. And so what this means is that in a compact metric space, if you take a decreasing sequence of closed sets, okay, and if each of the closed set is non-empty, then their intersection also must be non-empty, right. Something similar to what we have seen in the case of Cantor's intersection theorem. There also we had taken a decreasing sequence of closed sets, but there we assume something additional thing, that the diameter goes to 0 and then we had proved that the intersection consists of just one single point. In case of compact sets we need not assume anything about the diameter, the whole thing happens inside a compact metric space, okay, and then intersection also may contain more than one point. All that we can say is it is non-empty. So let us, since this is an important consequence, let us write that as a corollary, okay. So let X be a compact metric space, and let us say that Fi I belonging to I be a decreasing family of closed sets. Then if each Fi is non-empty, sorry, if each not decreasing family, let me say Fn, okay, instead of Fi, Fn n belonging to n be a decreasing sequence of closed sets, because if we take I to be any arbitrary indexing set, then decreasing sequence does not mean anything, because unless that I has an order, okay, we cannot talk about a decreasing, okay. So that is why we take decreasing sequence, okay. So decreasing sequence of closed sets, if each Fn is non-empty, then intersection Fn n belonging to n is also non-empty, okay. And this follows from this theorem in a straightforward manner, because if each Fn is non-empty, then this family has a finite intersection property, okay, right, okay, and hence intersection over the whole family must also be non-empty, okay. There are, in some books you will also find a statement, this same statement written in a slightly different manner, okay. What will be said is that if the intersection over a whole family is empty, okay, then intersection over at least, then there exists a finite subfamily over which the intersection is empty, okay, right. But you can see that that is basically same as this stated in a different language, okay. Or similarly here, okay, statement might be that if the intersection over the Fn is empty, then at least one Fn is empty. Of course, if one Fn is empty, all subsequent Fn's also will be empty, because it is a decreasing family, okay, right. Now coming back to the properties of compact sets, we have already shown that every compact set is closed, okay. We also want to show that every compact set is bounded. In fact, it is something more than bounded, it is a slightly stronger property, and we shall discuss that property now, okay. It is what is called totally bounded. It is a new term that we shall define, okay. So what is meant by totally bounded? This means the following, suppose you take A as a subset of X, okay. What is meant by bounded? We know that bounded in our metric space we have defined that a set is bounded if its diameter is finite, okay. Set is bounded if its diameter is finite, okay. Totally bounded means something more, okay. What we want is that what should happen is that if you are given any positive number, let us say epsilon, okay, then you should be able to cover this set epsilon by a finite number of balls with radius epsilon, okay, right. So we will say that A is said to be totally bounded okay, is said to be totally bounded if for every epsilon bigger than 0, what should happen is that there should exist a finite number of points in this A, and A should be contained in the union of open balls with center at those points and radius epsilon, okay, and this you should be able to do for every epsilon, okay. So for every epsilon bigger than 0 there exists a1 a2 an in A, there exists a1 a2 an in A such that A is contained in union let us say k going from 1 to n of open balls with center at ak and radius epsilon, okay. That is, you take open ball with center at a1 a2 etc each with radius epsilon, then A must be contained in the union, okay. And remember it is a finite union, okay. It is a, so that is important, okay. For every epsilon there should exist a finite subset of A, okay. Should exist a finite subset of A, and A should be contained in the union of open balls with center at those finite number of points, okay. In some books this set a1 a2 an is called an epsilon net, okay. Okay. Epsilon net means it is a set of, it is a finite set such that the given set is contained in the union of open balls with center at that points, okay. So such a thing is called an epsilon net, okay. And so the definition of total boundedness will be every epsilon has a finite epsilon net, okay. But we shall not use that terminology, okay. Now is it clear that every totally bounded set is bounded? Okay. Is bounded. Okay. Okay, how does one prove that? Suppose A is totally bounded, okay. Suppose A is totally bounded, okay. Then, okay, alright, suppose A is totally bounded, then what we know is that for every epsilon there exists some finite subset a1 a2 n, okay. Suppose I call that subset B, okay. Suppose I call this set B, let us say that B is a1 a2 an, okay. Is this clear that B is bounded? It is a finite set, so its diameter will be you take distance between a1 a2 a2 a3, that take distance between ai aj for all pairs a I and j, that will be finite number of real numbers, okay, finite subset of real numbers, take their maximum, that will be the diameter of B, okay. So diameter of B is finite, okay. So B is bounded. So diameter of B is finite. What can we say about the relationship between diameter of A and diameter of B?
Less than equal to.
Less than equal to diameter of B plus
This epsilon.
plus epsilon.
Maybe.
Okay, let us say, how does one prove that? To look at the diameter of A, what we should do? We should take any 2 points x and y in A, okay, and show that distance between x and y is less than or equal to that number, whatever is that diameter, okay. So suppose we take x and y in A, that x and y belong to A, okay, okay. Then we know that A is contained in this union, let us k equal to 1 to n, open balls with center at ak and radius epsilon, okay. So what follows from this? That each of this x and y is contained in one of those balls, okay. Okay, of course they may not be contained in the same ball, okay, they may be contained in different balls. So we can say that X is contained in some ball and Y may be contained in some other ball. So we can say that this means there exists, let us say, AI and AJ in A such that X belongs to open ball with center at AJ and or it is center at AI and radius epsilon, and Y belongs to open ball with center at AJ and radius epsilon. Okay. Okay. All right. Now what can we say about distance between X and Y? Okay. We can say the distance between X and Y is less than or equal to distance between X and AI, okay, plus distance between AI and AZ, okay, and plus distance between AZ and Y, okay, plus distance between AZ and Y, okay. Okay, this is less than epsilon, okay, right, this is also less than epsilon. What about this? This is less than or equal to diameter of B, okay. So we can say that this is the whole thing is less than or equal to diameter of B plus 2 epsilon, okay. So what does it prove? That diameter of A is less than or equal to diameter of B plus 2 epsilon, okay, okay, diameter of A. So diameter of A is less than or equal to diameter of B plus 2 epsilon, okay. So that proves that every totally bounded set is bounded, okay, and what is the obvious question to ask here? Whether, yeah, that's right, whether the converse is also true. Can we say that every bounded set is totally bounded? Okay. Well, obviously if that were the case, then we would not have defined the two things separately, okay, right. As I said, total boundedness is a stronger concept than boundedness. Every totally bounded set is bounded, but in general the converse is false, okay. Okay. But again, as you know, to show that the converse is false, we have to give a counter example, okay. All right. Okay. Giving a counter example is easy, okay. Again, as I said earlier also several times, when we think of counter examples, the best metric space to start with is a discrete metric space, okay. You start with a discrete metric space, okay, right. Take any infinite set and give a discrete metric on that, okay. Let us say, for example, we can take R, okay. You take R and D, where D is a discrete metric, where D is a discrete metric on R. Okay. Okay. Now, is this bounded? Right? Because discrete matrix distance between any 2 points is 0 or 1. Okay. So then diameter of R is 1. Okay. Okay. Therefore, R D is so R is bounded. Okay. Is it totally bounded? Okay. If it is not totally bounded, how does one show that? For some epsilon this should be false, okay. there should exist some epsilon such that this cannot be covered by a finite number of balls with radius. Okay, what is such epsilon?
By 2.
Yeah, you can take, for example, take epsilon equal to half, for example. Okay. Okay. If you take epsilon is equal to half, and if you take, let us say, any point in the real line, and if you take, say, open ball with center at x and radius this epsilon, what will be that? That will just singleton x. Okay, that will be just singleton x. Okay, right. And so if you take any finite number of balls like that, their union will be just a finite subset of R. Okay, that can never be R, right. So this is an example of a set which is bounded but not totally bounded, right. So total boundedness is a much stronger concept than boundedness. Okay, so let us again recall, total bounded means this: every totally bounded set is bounded but the converse is false. Okay. Now the question is, what has compactness to do with all this? Okay. What we want to say is that every compact set is totally bounded. Okay. Every compact set is totally bounded. Okay. Now before proceeding with that, let me also mention one more thing. Okay, in case of real line, or in case of R2, R3 or Rk with any of those metrics, in those spaces it so with the usual metric, not with discrete metric. Suppose if I take R with the usual metric, okay, then every bounded set is totally bounded. Okay, in R with the usual metric, every bounded set is also totally bounded. Okay, this happens in case of some metric spaces, it does not happen in case of all metric spaces. Okay. Let us just see why that should happen. Okay, now let us say R with usual metric. Okay, let us say R with usual metric. Okay, then every bounded set is totally bounded. Okay. Now how does one show that every bounded set is totally bounded? In let us say we are talking about R. Okay, so let us take that A is a, let us say that A is a subset of R. Let A be bounded. Okay. If A is empty set, nothing to be, okay. If A is empty set, it is obviously totally bounded. Okay, so this is, we don't have to bother about it. Okay, so assume A is non-empty. Okay, and because of our LUB axiom, okay, we know that if a set is non-empty and bounded above, it must have a least upper bound. Okay, and similarly, if it is non-empty and bounded below, it must have the greatest lower bound. Okay, so since it is bounded and non-empty, it means it is bounded above and below. So let us say that let alpha be equal to infimum of A, that is greatest lower bound, and beta be equal to supremum of A. Then A is contained in okay, then A is contained in the closed interval alpha to beta. Okay, A is contained in, and so if we can cover this interval alpha to beta by a finite number of open intervals, okay, then it will mean that A is totally bounded. Okay, and that is easy, right? For example, suppose though epsilon is given, let epsilon be bigger than 0 is given. Okay, and let us say this is alpha and that is beta, and A is inside this. Okay, so can we find a finite number of points in this alpha to beta such that they cover this interval, they cover this interval. In fact, okay, let me also say one more thing here, and we will come back to this, okay, we will come back to this, okay, and those two things I shall give to you as exercise, okay. Okay, one exercise is this, okay, suppose A is totally bounded and B is a subset of A, okay. Suppose A is totally bounded and B is a subset of A. What can you say about B then? B also must be totally bounded, okay. Then B is also totally bounded. In other words, every subset of a totally bounded set is again totally bounded, okay, that is one thing. Second thing is, if a set A is totally bounded, its closure is also totally bounded, okay. So if A is totally bounded, then A closure is also totally bounded. Okay, this is the exercise, okay, prove that. Okay, now what is the relevance of all this while discussing here? We will just prove that this interval alpha to beta is totally bounded, okay, right. That will mean that A is totally bounded, that is the idea, okay. We shall just prove that this interval alpha to beta is totally bounded, and because of this first part here it will imply that A is totally bounded, okay. Now how does one prove that this is totally bounded? You should given any epsilon bigger than 0, you should find points in this interval such that balls with centers at those points, in this case balls means open intervals, okay. Suppose there is any point x a1 here, then ball, it means interval a1 minus epsilon to a1 plus epsilon. Intervals like this should cover this completely, okay. Now what is the obvious way of going about that? Okay, we can start arbitrarily. For example, I can choose a1 is equal to alpha, let us say. Choose a1 is equal to alpha, okay. Then of course there is nothing like a1 minus alpha, so the first interval will be a to a, okay, let us say a1 minus epsilon to a1 plus epsilon, okay. Then let us say second point I choose as, let us say a1 plus epsilon by 2, okay, right. Then there will be next interval, etc., etc., okay. So idea is that if all of them should cover, okay, all of them should cover, what is the total length of all these intervals? Each interval is of length 2 epsilon, okay, each interval is of length 2 epsilon, okay. So suppose there are n such intervals, the total length will be 2n epsilon, okay, and so suppose we choose n such that 2n epsilon is bigger than this beta minus alpha, okay, then their union will cover this, okay. Of course you can choose the points appropriately, okay, that is we can choose the points in such a way that this next point is within this, that is the union covers the whole interval AB. In other words, what we can do is choose n such that 2n epsilon is bigger than beta minus alpha, okay. Can this be done always? Okay, again use the Archimedean property, okay. Whatever be these numbers epsilon and beta minus alpha and 2, you can always choose n such that n is bigger than beta minus alpha divided by 2 epsilon, okay. So choose any such n and then choose those n points and then show that there these n intervals will cover this given interval alpha to beta, okay. Is it clear? This can be done whatever be alpha and beta and whatever is epsilon. Okay. So given any epsilon, you can always find n points, let us say a1, a2, an, such that the intervals aj minus epsilon to aj plus epsilon, their union will cover this interval alpha to beta. So we can say that okay, I will continue here. We can find a1, a2, an in this interval alpha to beta such that alpha to beta is contained in union of say intervals aj minus epsilon to aj plus epsilon for j going from 1 to n. Okay. Okay. All right. Is this clear? So in R every bounded set is also totally bounded. Okay. All right. Can we do a similar thing in, let us say, R2? Can we do the, because whatever instead of the interval there, that will be some closed ball with some finite radius and some center. Okay. If every bounded set will be contained in some closed ball, okay. We can, so if you can show that every closed ball is totally bounded, just as here, see, remember, to show that every bounded set is totally bounded, it was enough to show that every closed interval like this is totally bounded. Okay. So similarly, if you can show in R2 that every closed ball with finite radius is totally bounded, then you will be able to show that every bounded set is totally bounded. Okay, right? And not only in R2 but R3, Rk, any of those spaces. Okay. So let me just say that in Rk with any of those metrics, take any of these metrics. Okay. There will be a small modifications in the arguments if you change the metric. Okay. But whatever be the metric you take in Rk with any of these terms, every bounded set is totally bounded. Okay. Okay. Okay, so let us again take a review of whatever we have shown about the compacts. We have shown that every compact set is closed, okay, and every compact set is also totally bounded and hence bounded. Okay, right. So let us just write every compact set is closed and totally bounded. Okay. Of course, it also means that every compact set is closed and bounded. Okay, every compact set is closed and bounded, and in real line with the usual metric, you can just replace this totally boundedness by boundedness. Okay. Okay. And what is interesting is that in the real line the converse is also true. Okay. What will be the converse? Converse is that every, okay, in since we are talking about real line, we can say every bounded and closed set is also compact. Okay, every bounded and closed set, and that is a very well known theorem that is known as Hein-Borel theorem. Okay, Hein-Borel theorem. Okay, in, let us say, in R with usual metric, a set is compact a set is compact, okay, if and only if it is closed and bounded. Okay, right. Actually, if a set is compact, that it is closed and bounded, that part is true in every metric space. In fact, something more is true, okay, not only bounded but it is totally bounded, okay. But what is particular about this real line is that the converse is also true, okay, and that is what is called actually Heine-Borel theorem, okay, that in the real line every closed and bounded set is compact, okay? And we already know that in every metric space if a set is compact it must be closed and bounded, and the importance of this theorem is that it gives us complete description of compact sets in the real line, okay. We can now recognize all compact sets in the real line. Compact set must be it should be closed and it should be bounded, and that is all, okay. Those are the compact sets. So now we have several examples. So for example, every closed interval, every interval like this, let us say AB, okay, that is an example of a compact set, okay. And you take any closed and bounded set, that must be compact, okay. We shall discuss the proof of this in the next class. We will stop with this today.